In this video, we'll cover the problem, open the lock. So you'll see we have a lock that consists of 4 characters. It looks something like this, the string 0000. Now each individual one of these right here is called a wheel, a circular wheel, and it has 10 slots, 0 through 9 inclusive. The wheels can rotate and they can wrap around. So this one can kind of go up to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it goes back to 0. Or we can immediately from 0 go kind of backwards, and that'll take us back to the 9, and then 8, 7, 6, and so on. And one move is turning one of these wheel slots. So for example, if we started with 0, 0, 0, 0, one move can take us to 0, 1, 0, 0. A second move can take us to 0, 2, 0, 0, and so on. And the fewest number of moves to get from all zeros to 0, 2, 0, 0 is exactly 2 moves. All right, we're given a list of dead ends. So these are kind of strings that everything freezes if we reach that situation, and that is like kind of a failure mode. If we get there, we're stuck, we can't do anything. And so given some target, representing a combination that we are trying to reach, something like this, we want to return the minimum number of turns or moves we need to make to start at our initial combination 0, 0, 0, 0 and end at this target combination. We should also be returning -1 if it's impossible to open the lock. Alright, so with this problem, we have a hidden graph, or an implicit graph, and I want to explicitly state the kind of properties of this graph. So in our implicit graph, you can imagine that our nodes need to kind of be entities, like states or pieces of core information that we're modeling relationships between. In this case, our nodes are going to be, again, our states, and our states are combinations. The combination of the lock is a node. For example, this could be one node. Then our neighbors, or edges, these are kind of related concepts. Our neighbors are all combinations we can reach from the current combination. So for example, the neighbors of 0, 0, 0, 0 would be 0, 0, 0, 1. We have 0, 0, 0, 9. And then you kind of do this for every position, right? So you could have 0, 0, 1, 0. You could have 0, 0, 9, 0, and so on. And these kind of continue onwards. But this is the implicit graph we have in this problem. We have a bunch of combinations, and they're kind of related to each other based on these properties we've defined here. And our goal is to find minimum turns to start at this combination and end at whatever the target is. So if you think about this visually as a graph, we are trying to find the shortest path between our start combination and our target combination. And we know how to do that. We'll do a level order traversal starting from our start combination, and we'll just kind of go level by level outwards. And the first time we hit our target combination, we will know that we have found the shortest path because of the fact that we're going level by level. So if there was some shorter path, we should have already seen it, meaning the first time we see it must be the shortest path. Okay, great. Now let's go ahead and start coding this question. It is going to be quite a lot to code. So first thing is we have our dead end set or array, but we don't want to check if a combination is in the dead ends array with something like dot includes, because that's going to be linear time with respect to the length of the array. And we're going to want to do these checks often. So I'm going to create a set out of these dead ends here. Now, off the bat, we know that there are 2 cases where we can immediately decide that it's impossible to solve the problem. So we can say, we can see if we include the start combinations, it'll be deadendset.has the start combination, which we'll add, and we'll have includes target, which will be deadendset.has again. Because if either the start or the target is a dead end, they'll never be possible to reach. So actually, I want to confirm if the target is in dead ends, what does that mean? I guess we would be able to reach the target, but we would freeze there. So we'll check if this is necessary. at the end. Now I want to define a constant for our start combination. We do know in this case that it is all zeros, but you never know. Maybe in the future that changes and we want a different start combination. It's nice to have it separated out as a constant. Plus, it makes it more readable than having some arbitrary string of zeros. Here it's like, oh, okay, clearly it's the start combination. All right, now we'll say, oh, and here we'll put target. If we include the target, that's also potentially an issue, but we're going to check if that's necessary. So if we either include the start or the target in dead ends, we'll return -1. We'll store that in a constant as well, just so we can have some English meaning to it. So we'll say impossible to open equals -1, and then here we're going to return impossible to open. Otherwise, now we can actually do a standard BFS. So we'll do get min turns, and we'll pass in our dead ends and our target, and that should be all that we need. All right, now we'll have our get min turns function that takes in dead ends and our target. Now, we want to write our BFS starting from the start combination, ending at the end combination. So we've seen this many times. We're going to create our queue. We're going to add to it the start combination. And we know with shortest path questions, we store metadata. So we're going to store the combination, which will be the start combination. And then we have to store num turns so far, which is going to be 0, I believe. Let's confirm. Let's see. Okay, so this sequence here is 1, 2, 3, 4, 5, 6, 7. Okay, so they're counting the number of edges, right? Because there are 7 nodes in this sequence and 6 edges, and the output is 6. So if we're counting edges, then yeah, we put 0 here. If we're counting nodes, we would want to start with 1 because the start combination is a node. But this should be good for now. Another note here is typically when you're defining your queue, you should also think about, do we want a visited set? And in this case, well, generally actually, you should be thinking about what kind of graph you have to determine if you want a visited set. If it's possible to have cycles, then it's important that you have a visited set so that you don't get stuck in an infinite loop. Our graph is actually undirected because if you have something like 0, 0, 0, 0, you can go to 0, 0, 0, 1, but also if you have 0, 0, 0, 1, you can go to 0, 0, 0, 0. Obviously, you can just kind of turn this in the reverse direction. So our graph is undirected. This means that we can have cycles. We know every undirected graph can have cycles, and sometimes directed graphs can also have cycles. So we're going to need a visited set to make sure that we don't have any infinite loops. Now, we're going to iterate so long as our queue size is greater than 0. We're going to have our 3 steps: remove node, process node, and add neighbors. Now, one thing to note, normally in shortest path problems, we're going to return inside of our process node step. However, there's one other case where we don't return at any point and we break out of our queue. And if we break out of this loop on queue size being greater than 0, and we have not yet found our target, that means that it is not possible to reach our target. So we need to return impossible to open. Now, I'm actually going to rename this to be target combination here, and for consistency's sake, we can do that everywhere. Okay, looks like we're good there. Okay, now in terms of remove node, this will be pretty straightforward. We'll destructure out our combination and our num turns so far, and that's equal to q.dequeue. Our process node, we'll come back to it. And our neighbors is going to be a little bit tricky here. So I'm going to write a separate function that goes through this and generates our possible neighbors. It's going to be, we'll just do get potential, or sorry, our potential neighbors is what I meant to say. And this will be a get potential neighbors function. It needs to know our current combination, and yeah, this should be fine. I think that's all it needs. And for now, we're just going to iterate over each of those. So we'll say for const potential neighbor, and these will all be combinations. They'll just be strings of this format here, the returned output. So it'll be an array of things like 1, 2, 1, 2, 1, 2. So for each potential neighbor in our potential neighbors, what are we going to do? That we'll simply add it to our queue. Potential neighbor. You know what? We can go ahead and call them neighbors. Let's see. Yeah, okay, yeah. So they definitely are still neighbors. I was thinking, like, are these actually neighbors if they might be dead ends or something like that? They are still neighbors. They might just be neighbors that we freeze at, so we don't want to include them. But here, we can name everything neighbors, and we should be fine. And we're just going to onqueue our neighbors, or add them to our queue here. Now, one thing to note, based on most problems, we'd add some checks here, like if it's visited, don't add it here. And we also want to make sure that we have, if we have a dead end, then we do not add it to the queue. Or at least we do not process it as a valid option. I'm not too sure about exactly why this happens, but for this problem in particular, when I put those checks here inside of the for loop, we get a bad alloc error on LeetCode. But when we put them in the process node step, everything passes. So we'll go ahead and stick with that for now. Okay, so we have the skeleton of our BFS done. We need to fill in this process node step, which is usually our core logic. So we can add our check. We know that if the combination is our target combination, we can just paste this. Then we want to return the number of turns it took. So we can do num turns so far. There are a couple other checks. If the current combination has already been visited, then we can continue. We don't need to do anything. If dead ends dot has our combination, if our combination is a dead end, then we cannot turn anything, so we continue. And yeah, this should be all of our checks. And we also want to mark the current node as visited so that future iterations will know that we visited this node. Now, there's one other point where we want to be a little bit careful here. It doesn't actually matter too much, but you can imagine that we found the target combination, but it's also in our dead end set. Then we should probably not be considering that something like a success case. We should not be returning. So I would personally put this check as the first, and I guess just for consistency, we can put the visited check there. It doesn't really matter too much. In practice, this doesn't really matter because we've already checked here if the dead end set has the target combination, but personally, I prefer to write it this way. Okay, I believe we've covered most of the work here. Should probably rename this get neighbors. Yeah, I think this is the main function. Now we need to write our get neighbors function. This is going to take in a combination, and we're going to return an array of neighbors. So we'll create an array here, and we'll do return neighbors. Then what are we going to do? We want to iterate over every character of our string. So we'll say I is going to be 0, I is less than combination.length, I plus plus. And what are we going to do? So if we have a string that's like 0, 1, 0, 1, and then we're on the 0th character, we want to say, all right, what if we were to go up? So we change this 0 to a 1. And what if we were to go down and change this 0 to a 9? So what we can do is, let's see, we can do this. We'll say const char is going to be combination at I. We can say const up char is going to be, we'll have a go up function, or can we name this better? What do they call it? Turn up? Okay, I think go up is fine. Go up from our char, and then we can have a down char, which is what if we go down from our char. And then we need, so that's just going to take us from 0 to 1, or this one will take us from 0 to 9. Now we need to construct the whole string. So we'll have a replace char at, let's see, we'll have combination at I, and then we'll pass in the combination. So this will replace the 0th char, for example, with up char. And then we'll do something similar. We'll have replace char at I. We'll pass in the combination. We'll pass in down char. And then we'll simply add both up string and down string to our neighbors. neighbors dot push down string. So this string is the result of moving whatever is at position I up, and this string is the result of moving whatever is at position I down. It looks like we need to capitalize this. Okay, now we have to write our helper methods. I'm going to kind of like at least define this sort of stub for every single one of them. I want to make sure we don't forget anything later on. So we'll do replace this. It's going to take in I, a combination, and a replacement char. Okay, we can do this one first. So we'll do string before, we'll do substring before I. Is going to be combination dot substring 0, I. And we can put a space there. We can do substring after I is combination dot substring I plus 1, and that'll go to the end of the string. And so this kind of gets the two pieces around what we're replacing. And then we can simply concatenate these. So we'll do the substring before I, we'll add our replacement char, and then we'll add our substring after I. You might be thinking about like what is the complexity of doing this concatenation right here. It doesn't actually matter too much. Our combinations are always length 4, so this would be like O of 4. It's not going to actually do anything for this problem. Okay, great. Now, given a char, we want to kind of go up by 1. Now, there's one case where we have the 9 string and we want to handle something specifically. I'm going to create constants so that we're not hard-coding strings. So we'll have our 0 string, which is going to be 0. And we'll have our 9 string, which is going to be 9. Now, the first thing we'll say is if we have the 9 string, so if char is the 9 string, just return the 0 string. We don't have to actually do it mathematically. Otherwise, we're going to say char as number is going to be parse int of our char, so we're just going to convert it to a number. We'll say const up char as number is going to be this guy plus 1, so we're just moving up by 1. And then we can say up char as string is going to be this number dot to string, and we'll return up char as string. So this is basically saying given some number like let's say 5, it's going to return 6. Given 2, it's going to return 3, all as strings. Given 9, it's going to return 0. That's the special case. Now we're going to do very similar stuff here. So we'll say if the char is the 0 string, if we're going down, then we want to wrap around and go to the 9 string. So we'll return 9 string. Otherwise, we'll do char. Actually, we can literally copy this part. Grab the char as a number. We can say down char as number. It's going to be char as number minus 1. We'll say down char as string is going to be down char as number dot to string, replicating the same stuff from above. And then we'll simply do this right here. Okay. Looks like we have finished writing out most of our methods. There's definitely quite a lot of code, so I'm sure there's a typo or something in here. But let's go ahead and see. If deadends.has. I bet we're passing in not the deadends set. Yep, that is a mistake. We should definitely pass in the set here. Interesting. So it looks like we're reading dot length off of nothing, off of null or undefined. Let's see here. Place chart I. What's going on here? Plus 1. Don't know if this is the issue. We can just add this here just to see if that fixes anything. Probably not. I think by default it fills in that argument. But let's see. Combination.length. And where is this happening? This is happening in let's see. I less than combination.length. So at this point we're passing in something that's not a string. Q.onKeyNeighbor. So that means one of our neighbors is not a string, which means upstring is not a string. Replacement char. Go up, go down. I think there is a possibility that I messed up this method, so I'm just going to do a quick check for that. We'll see. I'll just quickly reference our solution. It's probably not worth it to spend too long trying to debug this here. So I'll see if there's any core differences in what we're doing. New char int. Let's see. Before I, this looks similar. Most of this looks similar. Q. Okay, conceptually it looks almost identical. I think there might be some sort of detail I'm messing up. I'm actually going to try copying these functions over to see if there is some small implementation that I messed up. Let's see if that does anything. Oh, interesting. I've never seen this before. I'm just going to copy the code and then refresh the page. Not too sure if this is a LeetCode problem or if this is something else. This is a bit odd. We can test if my Wi-Fi is working. Yeah, it looks like my Wi-Fi is working fine. Okay, in the meantime, let's see. Looks like it's loading just slowly. But is there something I'm missing here? So one difference is that we are directly... You know what? No, we're not. Here's the problem. Okay. Yeah, when I add to the queue, I need to be adding an object, but I'm currently adding just the combination itself, but that's not the format of our queue. Okay, that makes sense. And because of this, here I'm adding just a combination. So then here, when we destructure out, we're destructuring combination from nothing. There's nothing to destructure here. We don't have an object. And because of that, combination is null. When we pass in to get neighbors, it's null. And here, when we do combination.length, we have a problem. That's what's happening. Okay. Hopefully LeetCode will let me get in so I can fix this. Okay, it looks like this might take some time. I'm pretty certain that that seems to be the main issue. So, okay, here we go. Does it save? No, we can actually go back. Nope, I don't even have the... I can't undo back to our old code, but same thing going on here. Here, what we want to do is we want to create an object that is combination, which is neighbor combination. I'm going to rename these to be a little better. And then we'll have num turns so far is going to be num turns so far plus 1. And let's name this, here we'll do for neighbor combination of neighbors. And let's see if that fixes our issue. Okay, looks like that works. And if we submit it, Let's see if there's any cases we missed. Okay, looks like that passes. Last thing we can do is check if this includes target is really necessary. It may not be. Ah, okay. Yeah, and then we have to delete and includes target from here. Okay, yeah, looks like that also works. Of course, the behavior is the same, so I'm going to see if I don't check dead ends before we find the target combination. Let's see if that matters. Yeah, okay. Looks like all three of these kind of have the same behavior. My personal preference is to write it like this, so I'll keep it this way, but does not seem to matter too much. All right, well, that's it for this video, and thank you for watching.